South Africa. A private game reserve. A film shoot. A cameraman walks in too close to a giraffe named Gerald, an animal that had spent years calmly appearing on camera and was considered completely tame. A split second later, the giraffe's head comes crashing down in one sharp motion, and the cameraman is thrown roughly 13 feet. A few hours later, doctors at a hospital in Johannesburg pronounce him dead. Multiple skull fractures and traumatic brain injury. And according to a wildlife expert who later reviewed the footage, if the blow had landed just a couple of millimeters differently, a student standing nearby would have died that same evening too. We grew up with the image of the giraffe as a symbol of gentleness, a cartoon hero, the most harmless giant of the Savanna. But that same animal can kill a lion with a single swing of its neck, runs blood pressure inside its own body that would rupture the vessels of almost any other mammal, and, as it turns out, isn't even one species. It's at least 4, which modern science had been mixing up for 200 years. Here's what we're going to dig into over the next half hour. How is a body built that can withstand blood pressure twice as high as a human's every single second of that animal's life? How did the gentlest herbivore of the Savanna turn out to be one of the few creatures capable of killing a lion with a single blow? Is it true that all giraffes are one species, the way we were taught in school? Or is that a long-standing mistake science only recently corrected? And the most unexpected question of all, is the giraffe really silent? Or has it been talking this whole time, just on a frequency we never thought to listen for? The answers will unfold gradually, chapter by chapter, and each one will flip your idea of this animal a little further than the last. The giraffe is the tallest land animal on the planet. An adult male reaches about 18 feet in height and weighs, on average, roughly 2,600 pounds, with the largest individuals on record approaching 4,300. Its neck alone, made up of exactly 7 cervical vertebrae, the same number humans have, except each one in a giraffe is stretched out to the length of a human forearm, weighs around 600 pounds, about as much as a grand piano. And a giraffe's heart weighs about 25 pounds and runs roughly 2 feet long, a size that sounds enormous until you consider how high that heart actually has to push blood. The vertical distance from a giraffe's heart to its brain runs about 6.5 feet, while in a human, the heart sits roughly a foot below the brain, and gravity, which barely registers as a factor for the human body, becomes a constant second-by-second engineering problem for a giraffe. How do you push blood up a 6.5-foot column of neck with enough force to keep the brain running, without rupturing the blood vessels in the head, and without letting blood pool in legs that sit several feet below the heart on top of that? We'll get into exactly how nature solved that problem and the price a giraffe pays for it every single time it bends down for a drink of water a little further on. But first, there's a stranger question worth settling, one that went unanswered for 2 centuries. How many species of giraffe are there, really? Ever since the giraffe was first given a scientific name more than 200 years ago, zoologists described it as a single species, Giraffa camelopardalis, with 9 subspecies, distinguished mainly by their spot patterns. Some populations have clean geometric spots with sharp edges. Others have jagged, star-shaped ones. And the differences were treated as roughly comparable to differences between dog breeds, or between color variations within the same species of cat, noticeable to the eye, but not significant enough to call them separate species. The problem is that this classification rested almost entirely on appearance rather than genetics, simply because genetic analysis on that scale wasn't available for a long time. And that started to change in 2016. when a team of researchers from the Giraffe Conservation Foundation and the Senckenberg Biodiversity and Climate Research Center in Germany carried out the first whole genome analysis of giraffe populations across the African continent. The result surprised even the researchers themselves. The genetic differences between separate giraffe populations turned out to be so deep that they're comparable to the differences between polar bears and brown bears, animals no one has ever considered the same species. According to that analysis, modern giraffes split into at least 4 genetically isolated lineages somewhere between 230,000 and 370,000 years ago. And since then, those lineages have essentially stopped interbreeding in the wild, even in places where their ranges overlap. Those 4 lineages are the northern giraffe, the southern giraffe, the reticulated giraffe, and the Maasai giraffe. And nearly a decade of further study later, in the summer of 2025, the International Union for Conservation of Nature officially revised giraffe taxonomy and recognized all 4 lineages as full species at the level of global conservation classification. To the average viewer, that might sound like a technicality that only matters to taxonomists. But this technicality carries real, practical consequences. 3 of the 4 newly recognized giraffe species turned out to be far more vulnerable than anyone realized back when every population across the entire continent got lumped into one seemingly stable total. The northern giraffe, for instance, turns out to be one of the rarest large mammals in Africa once you recount it separately. Somewhere around 7,000 individuals remain in the wild. And now that each species gets assessed on its own, conservation organizations can finally direct resources to where animals are actually on the brink of extinction, instead of wherever the paperwork looked fine simply because all the species were being counted together. So even the basic question of what a giraffe actually is was only properly settled by science very recently, within your own adult lifetime, not in some century-old textbook. And if science got something this fundamental wrong for so long, it's reasonable to assume other widely held ideas about this animal might also be incomplete or flatly wrong. Starting with the most physical one, how a giraffe manages to survive its own height. To push blood all the way up a 6.5-foot neck, a giraffe's heart has to generate pressure that would be diagnosed in a human as dangerously life-threatening hypertension. At rest, a giraffe's systolic blood pressure runs around 280 millimeters of mercury, with diastolic pressure sitting around 180, roughly double the normal blood pressure of a healthy adult human. And if a human heart suddenly started running at that pressure, the near-certain result would be a ruptured vessel, a stroke, or a heart attack within days, if not hours. In a giraffe, that pressure isn't a pathology, it's the baseline, simply what's required to keep the brain supplied with oxygen at all. The problem is that this same extreme pressure, so useful for the head, becomes lethally dangerous for everything below the heart. A giraffe's legs sit under enormous hydrostatic load, and blood at that pressure would, in theory, force fluid straight through the vessel walls into the surrounding tissue, causing swelling severe enough to make walking impossible. Evolution solved this almost like an engineer would. The skin on a giraffe's legs is unusually thick and tight, functioning like the compression stockings doctors prescribe for people with poor venous return, and it physically prevents the vessels from overexpanding and keeps blood inside the bloodstream instead of leaking into the tissue. The hardest engineering challenge, though, doesn't show up while a giraffe is standing still. It shows up the moment it lowers its head to the ground for a drink of water. Within a few seconds, the animal's head drops several feet, and the distance it had just been fighting gravity to overcome suddenly reverses, meaning the blood the heart had been straining to push upward suddenly gets a clear, unobstructed path to rush straight down toward the brain. In a human, a comparable sudden shift, hanging upside down for an extended period, can disrupt blood flow to the brain within seconds. But for a giraffe, this movement is a routine part of every single day, repeated dozens of times. The solution is tucked away at the very base of the skull, in a structure anatomists call the rete mirabile, the wonderful net. It's a dense mesh of small, heavily branched blood vessels that intercepts blood on its way to the brain and functions as a hydraulic shock absorber. And when the head drops and pressure spikes, this vascular network expands and soaks up the excess blood like a sponge, keeping the full surge from slamming into brain tissue all at once. When the giraffe lifts its head back up and pressure starts to fall, that same network contracts and pushes the stored blood back into circulation, keeping the animal from blacking out on the way up. And valves in the jugular veins play a supporting role too. A giraffe has an average of around 7 per vein, with some individuals running as high as a dozen, preventing blood from flowing backward once the head drops below heart level. What you end up with is a system of several independent but perfectly coordinated solutions. An oversized heart, compression stocking skin on the legs, a shock-absorbing vascular network at the base of the skull, and an entire cascade of venous valves, all working in sync every single time a giraffe wants nothing more than a drink of water. And if even one of these mechanisms failed, the result would be either a brain hemorrhage or a blackout at exactly the wrong moment. Say, right next to a watering hole, one of the most dangerous spots in the entire savanna as far as predators go. The story of Gerald and the cameraman who died, the one this video opened with, isn't some freak, isolated tragedy. It's a fairly predictable consequence of what an adult giraffe's body actually is, once you stop seeing it as a cartoon character and start seeing it as pure physics: mass, leverage, and speed. An adult male giraffe weighs more than a ton. Its legs end in hooves the size of a dinner plate, and the height from which that hoof comes crashing down gives it a speed and momentum that almost no other herbivore's kick can match. And, by some experts' estimates, a full-grown giraffe's kick can generate over 2,000 pounds of force per square inch, enough to crush a lion's skull or snap its spine in a single blow. That's exactly why lions almost never take on a healthy adult giraffe one-on-one. Instead, they target calves, sick animals, or exhausted stragglers, and even then, typically hunt in groups. A giraffe's neck, traditionally thought of as nothing more than a tool for reaching food in the treetops, is its second, far less obvious weapon. During mating season, males engage in a ritual called necking. Two rivals stand side by side and take turns swinging their necks at each other with full force, trying to knock the other off balance or force him to back down. And researchers who studied these contests closely found an unexpected set of unwritten rules. Giraffes turn out to be either lefties or righties in these fights, consistently preferring to strike from one particular side. And in most cases, they respect the same preference in their opponent, which makes a typical duel look more like a ritualized contest than a chaotic fight to the death. Even so, a blow from the full weight of an adult male's bony skull, equipped with its distinctive skin-covered knobs called ossicones, carries enough kinetic energy that in rare but documented cases, it has broken a rival's neck and killed him on the spot. The portrait that emerges completely contradicts the animal's cultural image. The cartoon giraffe is a clumsy, good-natured softy who, at worst, might accidentally bump into someone, while the real giraffe owns one of the most powerful kicks among all herbivores on the planet and carries a weapon on its head capable of killing one of its own in a fair fight. And yet, it rarely initiates aggression. In the overwhelming majority of cases, it would rather flee or step aside than get into a confrontation. And that combination of enormous latent power with almost no interest in using it is exactly what creates the deceptively gentle image behind which one of the savanna's most underrated animals is hiding. If a giraffe is this restrained and this eager to avoid conflict, how does its social life actually work? And how does an animal long considered essentially mute coordinate with the rest of its herd, especially in the dark, when eyesight stops being reliable? Science found the answer only recently, and it turned out to be more surprising than the researchers who went looking for it expected. For a long time, animal behavior science considered the giraffe essentially voiceless. Zoologists documented occasional sounds, snorting, grunting, short, sharp snuffles when alarmed, but nothing resembling a full, repeated vocalization, the kind of thing that lets elephants or wolves talk to each other. And one theory explained this on purely physical grounds. A giraffe's windpipe runs nearly 13 feet long, and according to some physiologists' calculations, the animal would simply struggle to push enough air through a tube that long to produce a genuinely loud sound. Among specialists, another, more exotic theory persisted for years. If a giraffe doesn't talk at frequencies humans can hear, maybe it communicates in infrasound, like elephants do. Vibrations so low the human ear can't physically detect them without special equipment. And the logic seemed sound. Both elephants and giraffes are large, social savanna animals that need to stay in contact over long distances. And infrasound, unlike ordinary audible frequencies, can travel for miles, bending around obstacles with almost no loss of signal. A team of researchers from the University of Vienna set out to test this, spending several years recording sounds giraffes made at 3 European zoos, accumulating nearly 1,000 hours of audio, recorded both day and night. And the scientists were specifically hunting for infrasonic signals, expecting to confirm the long-standing hypothesis. What they found surprised them in 2 different ways. First, not a single one of the recorded vocalizations turned out to be infrasonic. The giraffe infrasound hypothesis, repeated for decades as though it were close to established fact, simply didn't hold up once someone actually checked. And second, instead of infrasound, the researchers found something nobody had ever documented before. Giraffes produce a quiet, sustained, harmonically complex hum, a low, soft drone that falls well within the range of frequencies humans can hear, but so quiet and unremarkable that it had simply gone unnoticed through decades of observation. The most curious part is that this humming is almost entirely tied to time of day. The animals produce it almost exclusively at night, while the herd is resting or moving slowly through the dark. And researchers still can't say for certain what it means, whether it's a way of staying in contact when eyesight fails, a signal about the caller's location and condition, or simply an involuntary sound, something like a quiet snore. But the discovery itself speaks louder than any explanation could. An animal described as essentially silent for 2 centuries had been talking the entire time, just too quietly, and at the wrong hour of the day for anyone to be listening. Put it all together, and you get a portrait almost completely opposite to the one we grew up with. A giraffe carries a circulatory system running right at the edge of what a vertebrate's blood vessels can withstand, along with an entire cascade of independent engineering solutions, from compression stocking skin on its legs to a shock-absorbing vascular network at the base of its skull, any single failure of which would leave the animal unconscious or dead from hemorrhage every time it bent down for water. The weapon on its legs can crush a lion's skull, and the ritualized duels between males, for all their structure, sometimes end with one rival dead. Science got the most basic facts about this animal wrong for 2 centuries, treating as a single species what are actually at least 4 genetically distinct lineages that split apart hundreds of thousands of years ago. And even the voice the giraffe supposedly couldn't produce had been sounding every single night, just too quietly and at the wrong hour for human ears to catch it. The story of Gerald and the cameraman, the one we opened with, isn't a story about a randomly aggressive animal. It's a story about what happens when the physics of a massive body stops being scenery for a moment and reminds you what it actually is. A giraffe isn't a predator, and it isn't naturally aggressive. But it's definitely not the harmless, slightly goofy character it's been drawn as in children's books for so long. Which part of this surprised you the most? That giraffes turn out to be at least 4 separate species? The mechanism that keeps them from blacking out every time they bend down for water? The force of a kick powerful enough to kill a lion? Or the fact that they've been quietly talking to each other at night this whole time? Let us know in the comments, and if you're up for it, next time we'll dig into an equally strange question, the ongoing debate over why the giraffe's neck evolved in the first place. For reaching food in the treetops, or for winning those same ritualized duels we just covered.